So we are wrapping up chapter 14 today, essentially. And chapter 14 deals with trying to learn about the population mean or the population average from sample information that we have. So statistical techniques that come into play is working with the student t-distribution and then using that to construct confidence intervals for population means. And of course, it's also very important to be able to interpret those confidence intervals. So we will look through all aspects of this today. We did do a couple of examples of calculating values from the t-distribution in our last live Zoom session. But since that was a week ago, I thought perhaps the prudent thing today would be to just jump in and do, two more examples just on using the t-table. We'll be coming back to it over and over again today, but we're going to start with this example, just making sure everyone is comfortable reading the table. So on the screen share, you should be seeing the t-table at the moment. If you need a copy of this, there is one in the back of your textbook, but I've also uploaded this specific document to D2L. So under new course content, you can also access this t-table. So the first example today just says for each scenario below, calculate the critical value t star sub n minus 1 using the t-table. Now, A says for 95% confidence and a sample size of 22. So A says C% is 95%, and it says our sample size N is 22. Now, the degrees of freedom, which is in the subscript, that's N minus 1. So the appropriate row to use for the t-table corresponds to 21 degrees of freedom. And then secondly, what we have to figure out is whether to work with it one-sided, what alpha label to use. If I flip back over to the table, you'll see it refers here to t sub alpha, and it talks about two-tail or one-tailed probability. Now, what that's about is if we're saying C% confidence, what we're saying is in the middle of our bell curve, we want area 0.95, or we want the 95% of our probability to be in the middle. That means there's 5% left, which has to be split between the two tails. So the two-tailed remainder is 5%, but if you split it up between each tail, each one is only going to get half of that. So the value associated with one tail is 0.025. You only need one of these. You don't have to calculate both of them because if you look at the t-table, the rows will give you both the two-tailed and the one-tailed value. So in this instance, there's my two-tailed and one-tailed value. I just calculated 0.05 and 0.025 and 21 degrees of freedom. And so we just want to know what value we have where the row and the column meet up, which in this case is 2.08. So in this specific example, the t star value with 21 degrees of freedom is 2.08. Let's do one more. 99% confidence, sample size of 8. So that means our degrees of freedom are 7. And if we have 99% confidence, what's not accounted for jointly between the two tails is 0.01 because this is 0.99, which means the one-tailed value, you just have to halve that, that's 0.005. So we would look up the row corresponding to this two-tailed and one-tailed values, the column, and the row corresponding to 7 degrees of freedom. So let's do that. So 7 degrees of freedom and two-tailed 0.01. So let's just find the value in that row and column, 3.499. So in this case, T star with 7 degrees of freedom will be 3.499. So that's how we find the T star value. You're welcome to ask a question if you have any uncertainty about this at the moment. The application of this is going to be in the next problems we look at, where we specifically want to construct confidence intervals. So I'll wait a few more seconds before I start with the next example. But I think the context will also become clear if you're feeling unsure about the T distribution at the moment. So in our second example here, we are being told that we have a sample of 20 randomly selected observations obtained from a population that is normal. The sample average is 14.5 and the sample standard deviation is 8.1. So sample average, that's our Y bar value. Sample average is 14.5. Sample standard deviation is 8.1, so that's our S value. That's 8.1. Always remember, sample average is X bar or Y bar. Sample standard deviation is S. Those are, if we look at the 20 observations that we have, that means we calculated these from those 20 observations. And we want to construct a 95% confidence interval for the population mean. That's the quantity that we call mu. So mu is the true mean or the true average of the population. We want to know what that value is. And we want to make an informed statement about that using the information we've collected from our sample. So the confidence interval formula is given by Y bar plus or minus T star of n minus 1 times the standard error of Y bar. So what we need to calculate here is both the T star value and the standard error. So our standard error is just S over square root of n. So in this case, 8.1 divided by the square root of 20. And if we calculate that, and I round to, say, 2 decimal places, well, let me do 3 here, 3 decimal places, 1.811. For our T star value, we know degrees of freedom will be n minus 1, so 19. And since we're doing 95% confidence, that means our two-tailed remainder is 0.05, and the one-sided will be 0.025. So this just informs which row and column to use in the table. We need 19 degrees of freedom and the 5%, 2.5%. And so that gives us a value in this case of 2.093. So there's our T star value with 19 degrees of freedom, 2.093. So now we can plug in everything in our confidence interval formula and we can do the calculation. So my average is 14.5. My T star value is 2.093, and my standard error is 1.811. So I'm first going to multiply the T star and the standard error. That's 3.79. So that means my confidence interval is 14.5 minus 3.79 and 14.5 plus 3.79. All right, and we can use the convention of writing it in parentheses. That just tells us what the span of values are. So my 95% confidence interval is the values ranging from 10.71 to 17.79. Now, how do we interpret this? We would say with 95% confidence, the population mean is a value inside this interval. And let's just talk for a moment again about what that means practically. Firstly, well, let's see, someone has a question here. Oh, yes, it should have been 14.5. I messed up here. 14.5 plus 3.79. And so that'll actually give us 18.29. So apologies, that's the actual confidence interval. Yeah, I added the incorrect value there, so apologies. So let's talk about the interpretation. Firstly, can we say that the population mean is inside this interval? No, we cannot. We don't actually know. When you construct a confidence interval, at the end of the day, you never know whether it contains the population truth or not. This is just our best informed range of values. This is a range of plausible values. And what the 95% confidence means is that we are using a method that will work 95% of the time. So this could be the 5% of times where the method doesn't work and the true population mean is not inside that interval. But more likely, it's one of the 95% of times where it does work, and so it is inside the interval. Also, it's important to remember that the confidence interval doesn't tell you anything about individuals, right? It just tries to convey information about where the center of the population is, and the center as defined by the average. So it's trying to figure out if we could see the whole population distribution, where is the mean of that population? So it's not informative about what typical values look like for individuals that we sample from the population. It's making a statement about the center of the population overall. So does anyone have a question here about the confidence interval? I think it's easy enough to calculate. You've done the T-star thing a couple of times, so you can use the T-table to get T-star. The standard error calculation should be easy enough as well. So let's look at our next example. Systolic blood pressure in adults over the age of 50 follows a skewed distribution. A medical researcher takes a sample of 60 people from the population and measures the systolic blood pressure of each. The sample has a mean of 117.2 and a standard deviation of 16.5. Construct a 90% confidence interval. So first thing you should notice is you get told that you have a skewed distribution. Is this a problem for us? And the answer is sometimes it can be. You really, the formula for the confidence interval really relies on having a normal distribution or something that's approximately normal. So skew distribution is not close to normal. So that's a potential problem, but it's not as big of a concern because our sample size of 60 here is larger than 40. And that's a criteria I got from the lecture from yesterday, where it says if your sample size is very small, like less than 10, normality is very important. If it's between 10 and 40, you are still hoping that your population is symmetric. But once you're past 40, in terms of your sample size, then the original shape of the population doesn't matter that much anymore. Your calculation should be a good approximation. And so this is just an important check to do. I didn't talk through this on the previous example, but there it was stated that the population was normal. The moment you know the population is normal, you don't have to worry about what your sample size is. Okay, now the information we get given here, the sample has a mean of 117.2 and the sample has a standard deviation of 16.5. And we want to construct a 90% confidence interval. So this means at 90% confidence, the area or the chance not accounted for by the two tails is 10%, or if we just look at what's in one of those tails, it'll be 0.05. And of course, our degrees of freedom will be 59. So we need to find 59 degrees of freedom and this two-tailed equal to 0.1. So let's go to our table. Two-tailed equal to 0.1. But now we need 59 degrees of freedom. Now you'll see here, the table doesn't actually have 59 degrees of freedom. It has 50 and it has 60. But look at how close those values are to one another. You can run through the column, and as you go down, you'll see the values keep on decreasing, like they're consistently decreasing. And when we go from 50 to 60 degrees of freedom, they only decrease from 1.299 to 1.296. So those are very close to one another. And so even though 59 isn't exactly in the table, you can safely use the value at 60 because it is so close to, like you can see, just the actual entries in the table don't change a lot here when the degrees of freedom are large. So we'll use that value, and we were coming down the second column. So 1.671 is the appropriate value to use here. So this now gives us what we need to construct that confidence interval, y bar plus or minus t star times the standard error. So in this case, 117.2 plus or minus 1.671 times, and we need to do our standard error really quickly. This would be s over square root of n. So in this case, 16.5 divided by the square root of 60, which gives us 2.13. So our confidence interval is 117.2 minus, if I multiply those numbers, it's 3.559, and also 117.2 plus 3.559. So our confidence interval ranges from 113.641 through 120.759. Now, the question concludes by asking us, comment on whether it is plausible that the mean systolic blood pressure in this population is elevated. In other words, that the true mean is 120 or higher. So looking at this confidence interval, does it contain values that are 120 or higher? Yes, it does. So looking at this interval, it is plausible. And you can say with what confidence. In this case, it was 90%, right? It is plausible that at the 90% confidence level, we conclude mean systolic blood pressure is elevated. Because elevated would be if the mean was 120 or higher, and this confidence interval does include values of 120 or higher. So that possibility exists. It's not, the confidence interval cannot exclude the possibility of it being 120 or higher. Does anyone have any questions about this example? So one more example. Sample of 15 randomly selected observations is obtained from a population that is normal. So even though the sample size is small, population is normal, so we don't have to worry about things too much. Now, here is a new wrinkle though. The population has a standard deviation of 5, and the sample average is 10.2. So population standard deviation is sigma. We are being told sigma is equal to 5, and then we're being given our sample average as usual y bar equal to 10.2. Now, when you know the population standard deviation, it changes the calculation a little bit. Because sigma is known, we can use standard deviation and not standard error. Standard error is only an approximation of the standard deviation when it is not known. So the two previous examples, we relied on standard error because we couldn't calculate standard deviation. And the reason for that was we didn't know the population standard deviation. Also, when you're using the standard deviation, you're no longer going to use the T star value, you're going to use a Z star value. So what the confidence interval formula now looks like, this was not explicitly written down in the notes yesterday, so this is a good concept to take note of, is it'll be y bar plus or minus Z star times the standard deviation of y bar. Because of these reasons I just discussed. Since we can calculate standard deviation, that's what we should use. You should always default to that if it's available. And when you're using standard deviation instead of standard error, you associate that with a Z star value instead of a T star value. So let's calculate the components we need for this. Standard deviation, the formula is not going to look that different. It's just sigma over square root of n instead of s over square root of n. So in this case, 5 over the square root of 15 which is 1.291. Now let's look at how we get the Z star value. You can go back and use the normal table for this, but there's actually a way to get this out of the T table as well. 99% confidence means 0.99 is in the center of the bell curve. So the two-tailed remainder is 0.01, and the one-tailed remainder is half of that. So we will still use that specific row. So even though we're trying to find a Z star value, we're still going to use the T star value. The way you find the Z star value from the T table is you set the degrees of freedom equal to infinity. So let's flip over to this table, and if you scroll down far enough, you will see that option is in there. It actually goes all the way to degrees of freedom equal to infinity. So we need to use, in this case, infinity as degrees of freedom, and again, this column with 0.01 and 0.005. So finding where those meet up, 2.576. So even though it's the T table, it gives us a Z star value in the very last row. So here we have Z star is equal to 2.576. This now gives us everything to finish the confidence interval calculation. Let's plug in what we know. We know the sample average was 10.2. Our Z star value is 2.576. And we know our standard deviation is 1.291. So this is 10.2 plus or minus 3.326. So you'll do the same thing, subtract and add that to 10.2. When I subtract it, I get 6.874. And when I add it, I get 13.526. Again, does this mean that the true population mean is inside this interval? No, we don't know if the true population mean is inside that interval. What we do know is we're using a method that will be successful or will contain the truth 99% of the time. So this could be the 1% of the time where it doesn't work, but we know if we implement the same method consistently, it will work 99% of the time. So that's the confidence we have that this interval contains the true population mean.